Thank you very much. I'm still, after 2 days, impressed by this intro tape and the music. I guess that's the closest I will ever be to being a rock star. In fact, I'm not a rock star. I'm a physicist, far from being a rock star. More precise, I'm a material scientist. I was always fascinated by materials, and that for good reasons, because looking back on human history, materials always defined how people lived. Materials even gave whole time eras their names, like the Stone Age, where people used stones for tools or for weapons. A little later, a little more technology, people used this alloy here, made from copper and tin, bronze. A little later again, in the evolution of human technology, we used iron, forged iron, had some advantages. It is harder, makes better tools, makes better weapons. But it's not only materials that make a difference, but also the technology that arises from these materials. If you're thinking about the last few hundred years of our history, you think of the classical age. Romans conquered the whole continent with help of their technology that they used. Or a little later, in the age of discovery, people used technology, navigational skills, or the skills to build ships, to rediscover whole continents. So it makes sense to think about what is the technology that makes the difference today. What is the most influential technology? And I believe, or we believe, it's this here. It's the computer technology, IT technology. Whoever controls informations, whoever can process informations fastest, will have a strategic advantage in this world right now. So that gives the frame for the presentation I want to give you today. As Mitch already said, I want to talk about a little bit about computers, where we are and where we are going. I want to show you that we are heading into, or we're coming to a point where evolution of computer technology is a little bit stopping, and we are thinking about revolutions now. I'm going to show you why quantum computers might play a role in this revolution. I want to show you some concepts of quantum computers. And I want to show you what diamonds have to do with these quantum computers. And if you stick with me, stay with me through this quantum physics that we are talking about, I promise you that I give you the recipe for making your own do-it-yourself diamonds. So stick with me, and the second half of my presentation will bring you the recipe for homemade diamonds. But first we have to look a little bit back in computer history, I would say. And whenever we're talking about computer history, this is the diagram that is most important here. It shows Moore's law. Basically, last few decades, the time frame, and what we see here on the y-axis is the transistor count, the number of transistors on a microchip. So we started rather poorly, with a few thousand transistors on one chip, but that increased enormously. And in fact, that's what Moore's law describes. These transistors on one chip, or the number of the transistors, double every 24 months. And that's pretty accurate for the whole time that is shown here, up to now. A little different visualization of Moore's law is this here, because the question is, why was that possible to put more and more transistors on a chip? Well, fairly simple, because we made the transistor smaller. And that's shown here. We started with rather large transistors, 10 micrometers large, but we managed to decrease the size of these transistors, and they're much smaller right now. We had an era of simple scaling. We just improved the technology that we had to produce these transistors, and we were able to make them small, so that they just were 100 nanometers, for example. Then it got a little bit harder. We needed still scaling, but also innovations, new materials, new ways of packaging of the transistors on a chip to further increase the amount of transistors on such a chip. But if you're looking at this Moore's law diagram and we extrapolate this line that I show you here, you immediately see that we are heading into trouble. The trouble is that physics is, to some point, is dictating the lowest limit that we can reach. And the lowest limit is that I can imagine would be somewhere here, 0.1 nanometer. That's 1 angstrom, and that's roughly the size of 1 atom. It's hard to believe that transistors can get smaller than 1 atom, because at least you need something to be your transistor. So we're at some point getting into trouble where quantum effects will take a place because we're making them, the transistors so small that we cannot neglect any more quantum effects to take place. So what is that? What kind of quantum effects am I talking about? I want to give you a picture of what I believe these quantum effects are. This is a nice German Autobahn, and as you might know, the nice feature of German Autobahns is you can drive as fast as you like. That's not true. I have some points that in my... anyway, I'm not talking about my driving skills. The good thing is you can drive fast, and that works pretty fine as long as these cars stay on this side of the road and drive in that direction, and these cars stay on that side of the road and drive in this direction. Same is true for microchips. This is a microchip. If the electrons, our charge carriers that we are working with, stay on their lanes in their little tracks, everything is fine. But there is a problem if we are scaling down our transistors and getting into the regime where quantum effects take place. And this is a nice simulation by Jean-Christophe Benoit showing an electron here. This is an electron coming from the left, going to this barrier here, that's basically a wall, and you would expect that it's deflected. And most of the time it's just what happens. It is reflected to the left and would leave the picture again. But if you watch closely here on the right side, there is a faint whitish blob that's passing through the wall and continue to go to the right. And that is what physicists call quantum tunneling. At small scales, at quantum scales, something really strange is happening, and quantum tunneling is one of these strange effects. And we cannot avoid those quantum effects when we're really going to small scales. So the question is, if we cannot avoid quantum mechanics, why don't we use it? Why don't we build a quantum computer right away? And that's the first part of my talk now. We have to talk a little bit about concepts of quantum mechanics, but I will make it, I try to avoid mathematics, let's say. And the second part is we're trying to, I'm trying to show you concepts of quantum computers, how we realize them. So let's jump into quantum mechanics, and remember, if you stick with me, you're getting the recipe for diamonds, so it's worth to stay here. This is what's in all our German minds right now. It's the World Cup in soccer. And the player you see here is Manuel Neuer, our goalkeeper. We have some things in common. He's coming from my home city. We're coming from the same city. He's a little bit younger, and he chose a different career path. But nevertheless, he chose to be a soccer player. And no offense taken, but the game he's playing is fairly simple. He needs to know two information. He needs to know where the ball is, and he needs to know where the ball is going. That's all. That's a fairly simple game. This game would be more complicated if we go to quantum soccer, and I'm going to show you quantum soccer now. Very small kind of soccer. Now Manuel Neuer would have to choose what information he wants to have. Either he could choose to know exactly the position of the ball, then he has absolutely no clue where the ball is going, that makes it hard to catch it, or he can choose to know exactly the velocity of the ball, then he doesn't know where the ball actually is. So you see, quantum soccer is much more complicated than regular soccer. A personal note, maybe, that's why I think it's a little bit unfair that Manuel Neuer is earning millions, and me as a physicist, it's really hard to get a permanent position at a German university. So that's just some critique for our society, but anyway. Okay, let's stay here. We make it more scientifical now. We are leaving soccer for today. This is classical physics, just what I was talking before. It's perfectly fine to know the position and the velocity of a particle, of a ball, let's say. It's more complicated if we're talking about small particles, let's say an electron. Now we can know the velocity that this particle has, but then we have no idea where the particle, the electron, is. So that's this, this reddish blob that I drew here. We physicists like diagrams, so usually we draw a diagram describing this here, and it looks like this. This here, x-axis, is the position of the particle, so where it is. Where is the electron? And this here is the probability of the particle, so where can it be found? So it's very likely that it's somewhere here in the middle, but it may be that the particle is more to the right or more to the left. So that's the physicist way of describing it. And physicists even like equations more than diagrams, so that's the Heisenberg uncertainty principle here. It says basically the same. Either you can very exactly know the position or the momentum of the small particle, but both multiplied cannot be better known than this constant here. That's just a number. So you're limited by nature. And that's a really a concept that you have to think about it. This is not a limit because our microscopes or our devices are too bad, and we can maybe in 10 years, 20 years build a better device and simultaneously measure the position and the velocity. That's not the case. This is a principle of nature. This is an intrinsic uncertainty that really is happening, that describes nature on these small scales. But taking this diagram now, we already can explain quantum tunneling. Coming back to this wall I was showing you before, this is the electron coming from the left. And now we take this physicist's approach with this diagram, with a wall. And now you can already see it is, in fact, very likely that the electron is on the left side of the wall and it will be reflected to the other side. But there is a small probability on the right side that the electron is, in fact, already behind the wall. And that is exactly what you see in this simulation here. So on a quantum level, you never know precisely where a particle is. One picture I have to show you from yeah, that sounds a little bit awkward, but from the toilet of my physics faculty in Duisburg, I once found this picture here. Heisenberg may or may not have been here. I like that. That's physicist humor. Okay, anyway, that's just a quick joke. Now we're coming to another aspect of quantum mechanics. This uncertainty I showed you is not only true for positions or velocities, but also quantum states. So what are quantum states? Let's compare it to classical bits of information. So the classical bit can be either 1 or 0, on and off, if we compare it to light bulbs. Peter yesterday already showed us a good explanation of a qubit. That's now a quantum bit, and it has a interesting property. It can be in a superposition of both states. So it is both 1 and 0 at the same time. These superpositions are very fickle, so we need to take good care to not disturb this superposition, so we put it in a box and don't look at it. And Peter yesterday already told us, as soon as you look at your qubit, soon as you look at your superposition, you will determine its state. As long as it's in the box, it's perfectly fine. It's both 0 and 1. But as soon as you open the box, look inside and take a measurement, it will be either 1 or 0. And that's a remarkable difference to the situation I show here on this slide on the left. So if I flip a coin, that's always the scary part in a presentation. I'm always scared of flipping a coin and catching it in front of an audience. So I luckily caught this coin, and it's now on my hand. So is that a superposition now? No, it is not. This situation is described by the probability. Either it is heads or it's tails, and my ignorance, because I haven't looked yet. But still, the decision was already made, so it is either heads or tails. This is not true for our superposition. Saying that again, the superposition, there is no decision made yet. As long as you don't measure, there was no decision made. So that's really a superposition of 1 and 0. Okay, what is a qubit? Now I was talking about strange things that I call qubit, but what is it? So can we have some of these? Yes, we can, and I show you that. Again, with a comparison to classical bits. Classical bits, 1, 0, could be imagined like these spinning tops for children. So they could either be in this direction or upside down and spinning in different ways. If we're looking now at qubits, there is something similar in quantum mechanics that we assign to particles, and that's what we also call spins. So small particles eventually have spins. Nucleus, for example, electrons, photons, they have spins. You cannot imagine that as really like spins, like the electron is not really spinning, but they have an effect that we can use, and that's a magnetic field. So an electron, if you take an electron, it will have a spin, and that spin can be measured by a magnetic field. So the electron will have a north pole and a south pole. If you bring that now in a magnetic field, here's the magnetic field, then you can imagine the electron to be some kind of small compass needle. So the compass needle will align in this magnetic field. Obviously, the north pole will direct to the south pole of the outside magnetic field. And you also can invest a little bit of energy and twist your little compass needle in the other direction. That will cost you some energy, but you can do that. And please keep this image in mind, because that's what we later need when we build our quantum computer. We will actually twist our little magnetic compass needle in our quantum computers. So we can do that. If we want now to describe our qubit, we need two information, basically. How likely is it that the little magnetic compass needle is facing up? And how likely is it that it's facing down? That's the two informations you need to describe it. That's not very exciting, I would say. It's getting exciting when we use more than one qubit. Again, we're starting with a classical 2-bit system with these spinning tops, and this system out of 2 bits can have 4 states. Both spinning tops can be down, one can be up, the other one can be up, or both can be down, up. Was I starting with up? Or anyway, but you get the idea. So 4 states. If you want to describe the system you have to me, you need to give me 2 information. First information is what is the state of the first bit, and what is the state of the other bit. So 2 informations needed to fully describe this system. It's getting much complicated when we are looking at qubits. There are simple cases, so both qubits facing up, both qubits facing down. But this here, the entangled regime, that's a little bit more complicated. And you need quite some mathematics to explain or fully understand it, but I leave that out. I just try to explain it with my hands. So in that entangled regime, you have one qubit facing up, the other one facing down. And those qubits are perfectly free in whatever direction they want to take. So they can look in any direction they want, not just up and down, but any direction. Perfectly free, perfect freedom, with one exception. If the one qubit is facing in one direction, the other one is facing in the opposite direction. So that's the basic idea. So you see there are more possibilities where how the qubits can be, or in what direction the qubits can face. So what you need here to explain this system is you need 4 information. You need this information A, B, C, and D, 4 information for 2 qubits. And it's getting more and more complicated if you have more entangled qubits. It's really getting complicated if you look at this diagram here. This here down, the blue line is the classical bit situation, not getting much more complicated with more bits. But this here, this qubit system gets really complicated, and this is the equation 2 to the power of n. So the more n's qubits you have, the more complicated your system is getting. Or you can formulate it the other way around. The more qubits you have, the more complex the problem is that you want to describe with your entangled qubit system. In fact, if you have 300 entangled qubits, you need more information to describe this system than we have atoms in the universe. So these systems are really getting complicated and have the capability of describing complicated problems. One more thing. If we're talking about entanglement, and Peter yesterday showed us that calculations are really fast, or information flow is really fast with qubits, entangled qubits. So in a classical 8-bit register, if you want to do calculations, if you want to rewrite a register, you need time, because you need to address every single spot in this register. In qubits registers, that's a little bit different. We have this entangled system of qubits, and if we measure one or modify one, that will immediately take an effect on all other qubits too. So if we modify one, immediately we are changing all the others. Right? As I told you, they are not independent of each other. So, and yesterday we already heard that you could, even if you have 2 entangled particles, you could take the one and put it in one galaxy, and you have the other one, put it in another galaxy, and they are somehow communicating over those long distances. There was this story that Einstein didn't like this concept at all, because there was no limit of speed, like he was believing, like this upper limit of speed would be the speed of light. So he didn't like this concept at all, and even other physicists like Niels Bohr here, he said, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. So relax if you have some problems to understand it. Niels Bohr was one of the founders or inventors of the quantum concept. So it's no wonder that we have problems to fully grasp it. But I want to show you, you could ask the question, are quantum computers faster than regular computers? Well, I would say no. They might even be slower, but they have advantages. They have advantages when it comes to complex problems, where you need a lot of calculation steps to get to a result. One of these problems is this here, the traveling salesman problem. Very easy problem. And you would expect that there is an easy solution for that, but it is not. You have this traveling salesman here, and his task is to visit cities. He's supposed to visit all these cities, but every city only once, and he wants to find the shortest way between those cities. This problem is, you see, if you increase the number of cities, there are a lot of possible routes that this guy can take. So if you have 2 cities there's only one route, that's easy. But if you have 5 cities, there are 24 routes that he can take. That's more complicated, but I guess we all could find the easiest and fastest way. But 10 cities, 362,000 possible ways he could take, and even 28 cities, 10 to the power of 28 possible routes that he can take. If you would take a classical computer and test any possible route he can take and compare the length of them to find the best, and that there are more powerful algorithms out there to do it than brute force, but anyway, let's just imagine that you would do it the stupid way and really calculate any possible route. Brute force classical computer, 10 cities would take you 0.3 milliseconds. Well, that's fair. You're just jumping into your car and calculate the best way and go. 20 cities, 32 years. Well, that's a whole lot of preparation before you can go onto your business trip. 28 cities, older than the universe, not solvable by classical brute force computing. So this is a problem that's out here. So that's, I mean, that's not some kind of fancy problem. That's an everyday problem that I would expect to be easier to solve. And another problem, by the way, is cryptography. Yesterday we heard a whole talk about that, but just telling you our cryptography is based on a method where we use prime numbers, or is based on the fact that if you're multiplying prime numbers is really easy. Everybody in elementary school actually could do it, at least with a pocket calculator. But if I would ask you, what are the prime numbers that if you multiply them, give this number, that's increasingly hard. And it's even getting more harder when you increase the size of the number. So usually we take 1024-bit numbers, and that would take us some years, some 1,000 years to find the prime numbers. And that's what our cryptography right now is based on. Quantum computer, because I told you needs less steps to calculate these kind of problems, would do that faster in minutes. And that, of course, is some kind of danger for our whole security systems. Okay, we skipped that, but coming here, I want to show you now what do you, or we now see what we need. If we want to build the quantum computers, what we need is qubits. They need to be trapped because we want to keep them in place so that we can work with them. They need to be detectable. We need to get, it has to be possible to get access to them. And we want long coherence times. That's something that we yesterday already heard about, those superpositions, and I said that they're really fickle, so slightest disturbance will lead to a collapsing of them. So we need them to have long coherence times so that they keep their superposition for a long time. So how is that possible? Right now, it's hard. It's really hard. I call it badass physics. You need really huge machines. You need to cool down your chambers. You need to trap like electrons or the nucleus of atoms at a certain position. So you need magnetic fields and all this stuff which is expensive and huge. So it's really hard to imagine that anything like this will ever end up on your office desk, for example, if you like to buy something like that. So physicists were always looking for alternatives, better solution of these concepts. And they were pretty surprised, and I was also pretty surprised because I was working with this material for quite some time, but never thought about such an application. They were pretty surprised to find it here, in diamonds. Fairly regular single crystal diamonds. Although with some modifications, and I like this quote here from a physicist again, Colin Humphreys. He said, crystals are like people. It is the defects in them which tend to make them interesting. And that's what we are looking here today. We are looking at perfect crystals with some defects, but defects just like we want them to be. And to be more precise, we're talking about defects that we call NV centers. Why are they called NV centers? Well, this here is the perfect diamond crystal. And now we're bringing in some modification. This here is a nitrogen atom on one specific position in our crystal. And right in on the next, I haven't said, that's carbon here. Diamond is made out of carbon, so these are all carbon atoms. This is nitrogen, and the next neighbor is a vacancy. So there is one atom missing. So if you have this kind of defect, specific defect, a nitrogen next to a vacancy in a diamond crystal, you have something which is pretty neat for us to work with, because this is a trap for electrons. You remember, electrons have a spin. Electrons could be our qubits. So we have a trap here where we can trap in a diamond crystal an electron. And electrons have a long coherence time in diamond. Why is that? Because diamond is made of carbon, very light element, but the bonds between those carbon atoms are very, very strong. So what would disturb our electron, our qubit in this crystal, would be lattice vibrations. So the crystal, like moving, phonons is that we physicists call it. So lattice vibrations would disturb our qubit. But there are basically no phonons, no lattice vibration at room temperature for the diamond crystal. So that could be our material to realize qubits at room temperature on your office desk. But we said something else. We need not only the qubits, but we need also to make them detectable. So how can we detect our qubits in a diamond lattice? Well, we do what physicists usually do. We shine light on it. We shoot with a laser on it. And what you see then is we have some kind of light coming back. And this light can be detected with spectrometers with spectrometers. And what you see here are single NV centers in our diamond. So now we have an information. We get a light coming from these NV centers, and that's the information, or that's our way to detect our NV centers. Now, coming back to everything I told you about quantum mechanics, you remember we have this spin in our qubits, and we want to put them in one direction or in the other one to make it a 1 or a 0 or a superposition. I'll show you now how we do this in diamond. So this is the electron on the ground state. What happens, and maybe you remember that from your physics class in school or college, if we shine light on it, it will get excited. It jumps up on an excited energy level, and eventually it will jump down and will give off this energy that I was talking about, this fluorescence light here. So we will detect this light, and this is our our 1. Now we change we do the same experiment, but we change it a little bit. We start again with the electron on the ground state, but now we give it a small notch by microwaves, a small bump of energy. What happens here is then we lift it a little bit energy-wise. In fact, we turn its spin by that. You remember this compass needle in a magnetic field that I was talking about? You need a little bit energy to turn it in the other direction, and that's exactly what we do here. We use a microwave pulse to turn the spin up. Now we do the same experiment like here on the left side. Again, we shine laser light on it. The electron jumps up to the excited state. But now something else is happening. It's not directly jumping back on the ground level, but it takes, for a short time, an intermediate level and jumps back from that. The funny thing about this here is there is no detectable light now, or at least not in the frequency that we are looking at. So you see now we will getting a different signal. Either our spin was up or down. So we have a qubit, we can write it, and we can detect it, and we can write and read it. So this is all we need, and also what we also can do is if we make this bumping of microwave energy, this pulse of microwave energy precise, we can also make a superposition of this for this qubit and have this superposition that we want to work with. Okay, seems like everything is fine. We only have diamonds. That is, of course, a problem. Not every physicist has huge amounts of diamond in their laboratories, but this is where we are coming closer to the do-it-yourself part of this presentation, because can we find diamonds that are suitable in nature? No, because there is a problem with diamonds in nature. First of all, they are pretty rare and expensive, but most of all, they are dirty. They have inclusions, elements that are not supposed to be there if we want to have these super clean diamonds for quantum computing. So we cannot use these. Can we make our own diamonds? Well, what comes handy when we're talking about making own diamonds is this here. It's a phase diagram of carbon. What you can see here is this is all carbon, but in different forms. So at low temperatures, at low pressures, carbon likes to be graphite. We cannot use that. What we want is this here, this regime up here, it's diamond. And it's not surprising for you what you need to make diamond. It's really high pressure and high temperature, because that's what nature basically does. It takes carbon, presses it really hard, uses energy, temperature, and makes diamond from this carbon. Can we copy that? Of course. People doing that. These are large presses, commercially available and industrial used presses, to actually take graphite, put it in some kind of capsule, press it really hard, add some temperature, wait some days, and these things here will fall out, diamonds. I think they are beautiful, but unfortunately this yellow color comes from vast amounts of nitrogen in the diamonds. And although we want to have nitrogen for our qubits in the diamond, we don't want so much nitrogen in the diamond, because if you have so much diamond, the qubits will interfere with each other, and you will never be able to use this as a quantum computer. So the idea was, if we cannot use the method that nature is using, why can we find another method where we actually taking small building blocks and putting together our perfect diamond crystal? Just like my son would play with Lego and using these Lego bricks to build new structures, couldn't we take single atoms or molecules and put them together to a perfect crystal? Well, in fact, that's possible. The question is, where are you getting the carbon from that you need for the diamond? And we take simple gases. We need hydrogen and we need methane. And that's the reactions that are happening then in our gas if we in fact add some energy. Add some energy and you will break this hydrogen here and have atomic hydrogen. And this atomic hydrogen eventually reacts with the methane, CH4, and you will end up with hydrogen and a radical CH3. This radical CH3, as I will show you later, wants to find new binding partners and goes together and builds a larger crystal. And if you choose the right properties, I would say, you will end up with a diamond crystal. And I started, I would say, like 10 or 15 years ago with making my own diamond, and back then with a really simple approach. And this simple approach looks like that. I have to go back one slide, because I said we need energy. What kind of energy is that? This is the simple approach that we were using back in the days. The simple approach of bringing in energy in this process is, of course, a hot filament, simply heat. And this device here has the complexity of a light bulb, actually. That's why I put a light bulb next to it. You have this hot filament, the hot wire, basically made out of tungsten, for example, or molybdenum. And you have the gas coming from above, streaming next to the hot filament or over the hot filament. And at the end, you will have diamond, after the process, diamond on your substrate, if you have a good substrate like silicon, for example. It's really that easy. It's so complex, or it's as complex as a light bulb. That's how it looks in the laboratory. This approach is fine, but has some disadvantages if you want to have this really ultra pure diamond, because this hot filament is really hot. It has like 2000 Celsius, and that's close to the evaporation temperature. And so what happens is that you, during your process, a little amount of this metal will evaporate all the time. And that metal will be in the end up in your diamond films that you will deposit. So this is a nice approach if you just want to make diamond. But if you want to make perfect diamond to impress people or to make quantum computers, you need a little more sophisticated device. And that's our device here. That's a microwave plasma reactor. Microwaves, actually the same, more or less like you have in your kitchen, because it has the same wavelengths, it has the same power. But the tricky part is that here, we use slot antennas to couple those microwaves into our chamber, in the center of our chamber. And by coupling it in and having this strong electromagnetic field, we produce a plasma there. But the idea is still the same. We're bringing energy there in to break our process gases and to deposit diamond in the end. So I promised you the recipe for diamond. Here it is. You need your microwave. You need 99% hydrogen. You don't need the microwave. I just told you you also could use this microwave, this hot filament approach, this light bulb approach. You need 99% of hydrogen, 1% of methane, not too much methane, 200 millibar, so a little bit below our ambient pressure. It works like a charm on diamond, so it would be good if you have a diamond substrate, but it also works on silicon or any other, or not any other, but other metallic surfaces. But if you really want to grow single crystal diamonds, like I will show you in a couple of minutes, then diamond substrates would be nice. 800 degrees temperature, so the diamonds need really, or the substrate really needs to be hot. And then you need time, 5 hours, 5 days, whatever amount of diamond you want to make in your kitchen later this evening. What happens then is this here, you're starting with your gases, you're breaking your gases, just as I have explained to you. This is the CH3 and this is the atomic hydrogen. And then we are offering this diamond substrate, and the CH3 will settle on this substrate and continue to grow our diamond surface. If you followed the presentation closely, you could challenge me and say, well, you told us you need high pressures and high temperatures to make diamond. Why is this do-it-yourself approach working? Well, it works. We are still here. Huh? We are at elevated temperatures, but still our pressure is low. It is below atmospheric pressure, actually. So why are we not ending up with graphite? Well, I haven't told you everything that we need this atomic hydrogen for. I told you that we need it for the generation of the carbon radicals, the CH3, but the hydrogen has a much more important job to do. Because, in fact, it is true. Mostly we will deposit graphite and only small amounts of diamond, but still we use the hydrogen for etching the graphite that is growing, and the atomic hydrogen is very effectively etching the graphite and not effectively etching the diamonds. So in the end, by this etching effect, in the end we will end up with diamonds on our substrate. So that sounds really theoretical, but so that's why I want to show you a video of our diamonds actually growing. So this is our plasma reactor. This is a video shot from our process. You see here, this is the plasma ball, this greenish light. These are diamond substrates. very thin diamond substrate. The diameter is 10 millimeters, 1 centimeter, and the height here is about it's about half a millimeter. So very thin diamond plates. You see that they are reddish glowing, so that tells us that they are hot, rather hot, about 800 degrees. Now I try to start the movie, and what you see here is then, unfortunately it's not real time, this movie was taken in the course of 3 days. Take a look at this diamond here, because you see these growing waves going over the substrate. I like this video. So you see the diamond actually growing during 3 days, starting with half a millimeter, ending up with 3.5 millimeters. And although the edges here look polycrystalline and they're not really nice, the center here, this is really pure, perfect single crystal diamond. So I was, of course, curious how they would look like, because they are shabby when I put them out of the chamber. They are black. I know that they are perfect inside, but you cannot see it. So I laser cut this ugly stuff away and went with them to a shop where they polish crystals. And I asked them to make a brilliant cut and polish them like a brilliant for like you would put in rings or something. So I asked them to do that for me, but the guys there were, they were suspicious because they had never seen such a material. So they asked me, what kind of material is that? And I told them it's diamond. They still were suspicious because natural diamond also looked different. So they asked me where I have it from. So I said, I made it by myself. So that didn't help establishing a good... anyway, they were suspicious, but I found people to polish these stones, and they look beautiful. These are homemade, do-it-yourself diamond crystals, half a carat. I would say it's like 5 millimeters diameter, so they are really perfect. And talking about do-it-yourself and hacking, I used them. I was hacking my own wedding, actually, because this is a necklace my wife was wearing during our wedding, wearing a necklace with self-made diamonds. So whoever said that physicists cannot be romantic? So anyway, okay, we can make perfect diamonds, but we don't want to have perfect diamonds as long as you're not trying to make weddings. This is the perfect crystal, diamond crystal we were starting with, but remember I told you we need to get these NV centers in there. How are we doing that? Okay, we're taking our perfect diamond crystal, and then we're taking our ion guns, and I love this moment in the presentation every time, because especially if you're talking in front of kids, they're really impressed that physicists have something like ion guns. So we're taking our ion gun, and we're shooting nitrogen ions on our perfect crystal. What happens then is these ions, these nitrogen ions, are implanted in our perfect crystal, and also you will have some kind of defects, vacancies, and then we make some kind of temperature treatment. We just heat up the crystal to 700 degrees, and those defects, the nitrogen and the vacancy, will meet by itself without doing anything except adding energy, temperature. This is one way of doing it, and the other way of doing it is we are growing diamonds. I just explained to you how we're doing that, and at one point eventually we add to the growing process. I told you we are using hydrogen and methane, but at one point we add a small amount of nitrogen and continue to grow. And in the end, we will have a crystal with a small layer of nitrogen inclusions in our crystal. And then we take our electron gun, we also have something like that, and shooting on our crystal. And with electron guns, you can bring in vacancies in our crystal. And then again, this temperature process, healing of the crystal, and nitrogen atoms will find the vacancies, and we have our nice nitrogen vacancy centers that we can use for quantum computers. And people actually did that. This is my, I guess, final slide. people did that. We are at really early stages of realizing these concepts of quantum computers with diamonds. But in April 2012, I'm sparing you the details, but there was a 2-qubit diamond quantum computer running, and it was proof that they could actually make calculations with that. In fact, decoding a current code cryptography would take us 4,000 qubits. We are a little bit away from that, but still, we're starting to work on these really new concepts and strange concepts. And I personally find it really fascinating that starting with these strange concepts of quantum computers, we can actually realize devices from that. And people are interested in that. As you see here, 2014, Edward Snowden had a document stating that the NSA runs an 80 million research, I like the name of it, they have cool names for their projects, penetrating hard targets, to develop a quantum computer. So people are starting to, they see the potential in these kind of applications, so people starting to work on them. I want to finish with one quote. We are going back. We started in the early history of human mankind, and we are going back some 1,000 years, 2,000 years basically. This guy here, Plinius Secundus, he was making some kind of top 10 list of the most precious materials at that time, 2,000 years ago. In this top 10 list, there are some materials that we would expect. There's gold in there, there's silver in there. There are some materials that we wouldn't expect. There is a hard wood that he put in this list because the Romans like to make this huge office desks from this wood, so that is a bit surprising. But on top of this list, on top of this top 10 list of most precious materials, he put diamond. And he said a nice sentence. He said, "Maximum in rebus humanis, non solum inter gemmas, pretium habet adamas." I tried to translate it. My Latin is long ago, but if you translate it, it's something like the highest in all human affairs, not only in gemstones, that is the diamond. So, and with that thought, I want to finish my presentation. I like the idea that 2,000 years ago, diamond was the material of choice. 2,000 years later, in a really high-tech application, again, we're looking at diamond as the potential material. Thank you very much.
Well, we have just a few short minutes for questions. Anyone have a question? I'll bring in the mic. There.
Do you expect a price revolution for diamonds?
The question is if the price is dropping, if everybody's able to make their own diamonds, or? Yes. Of course, that is the biggest fear of anybody who is dealing with diamonds, with natural diamonds right now. And people don't like it at all that scientists are starting to grow their own diamonds. They are pretty scared, actually. They are fighting a fierce battle to distinguish between laboratory-made diamonds and natural diamonds. So they try to investigate if they can see either they're coming from a laboratory or from a dark mine in Africa.
Sorry, I didn't quite understand why a quantum computer would need less steps.
Why it needs less steps because actually because it can calculate in parallel. So the concepts of quantum computers, I spared them actually a little bit here to not fully extend my time. But the basic idea is that a lot of calculation is done parallel and not sequential. So that's in short, basically.
How hard exactly is it to actually make diamonds with a microwave oven and some DIY vacuum pump equipment? And why don't we have a diamond making machine in the foyer right now?
Yeah, maybe I was actually thinking. So I wouldn't advise people start using or producing diamonds tonight in their kitchen and start experimenting with hydrogen in their kitchen. So please don't do that, or at least don't mention my name. But I mean, this microwave plasma source is quite fancy. But this approach with the hot wire, this older solution, by the way, that was invented in the I think 70s or even 60s. We could. Or you could easily do something like that. You need some kind of power supplies, you need gas and a vacuum pump, and you can make diamonds. But of course, we're not making single crystal diamonds then, but more like polycrystalline diamond surfaces. So, but still, you could make diamonds, yeah.
And can we use a normal 2.4 gigahertz magnetron for microwave oven?
Yeah, you can. The generator would be fine, but you need the tricky part is the resonator, where you have the slot antennas and you couple this, you have the specific mode to couple the microwaves in and have this high electrical field in the middle of your plasma chamber. The generator is fine, would be fine, yeah. But you need some tricky adjustments to couple it inside your vacuum chamber. But frequency and power is the same like what you have in your kitchen, yeah?
So I'm sorry we're out of time now, but thanks for that talk.
Yeah, thank you.
And,